Hi. My name is Elchanan Hoffer Horneman. I'm an aerospace engineer. For the past 6 years, I've been a CFD engineer performing fire and egress analysis with FDS and Pathfinder. I am also the professional coordinator and R&D for our CFD department. I work at Netanel Engineers and Consultants, and we are the lead fire safety and CFD consultants for the project that I'm going to be talking about today. That is the Green Line of the light rail train in Tel Aviv. Bit of background about the project. The Green Line is a trainway spanning about 39 kilometers. In the picture, you see that out of that, about 4 kilometers pass underground with the twin bore tunnel. That's about 2.5 miles for the Americans here. Along these tunnels, there are 4 underground stations, and I was required to perform analysis for both the underground stations and the tunnel. Coming to perform this analysis, I have a few approaches that I could take. First of all, you could just do everything 3D, but that would take a long time and a lot of computer resources. You could put in your 3D model only what you're interested at, and at the boundaries of the 3D model, you would have vents, and in those vents, you would have flow from 1D simulations. Now, on these simulations, a bit of explanation there. They represent tunnels and stations as line segments and calculate one-directional flow through those line segments. So it's really easy to set up. You get the results in a few seconds. But using those as boundary conditions is something that should be considered for a few reasons. First of all, those results are steady state. That means that I will not know how the flow field is ramping, and I am very interested in the transient phase. That's where egress happens, right? Secondly, because the flow is fixed in those vents, then I'm not going to get any reaction to changes in the flow field. And finally, if somewhere in the model the flow is not one-directional, then those results may not be valid. That brings me to the approach that I used here. It's called the multiscale approach. In the multiscale approach, you have your 3D model, which has everything that you're interested at. All the other things are represented by 1D calculation that is embedded inside your 3D model. So it's going to ramp together with the flow field, and it's going to react to changes in the flow field. To run these simulations, I used FDS, and FDS has the HVAC name list. HVAC stands for heating, ventilation, and air conditioning, and the HVAC name list in FDS was designed to simulate HVAC systems in a 3D model. So you can put fans, dampers, ducts, vents, everything you need for ventilation systems. It uses 1D calculation, and it is solved simultaneously with the 3D model, so it's a good candidate for the multiscale approach. The use of HVAC in FDS for tunnels specifically is something that was actually validated and compared to experimental results with good agreement. Still, for a project like the Green Line, it was kind of complicated adjusting those boundary conditions. So let's talk about the general model layout. So like I said, we have the main 3D model where all the action happens, fire and egress. And then at the ends of that 3D region, we will have the HVAC components representing tunnels and stations that we are not really interested at except for the flow coming through them. Then at the ends of the tunnels, there are portals. Now, generally speaking, the flow in the portals is not necessarily going to be one-directional. That's why I felt that they should be part of the 3D solution. What you see here in the picture is one of my early tries at a station simulation. Now you can see it's large, it's complicated. What I did, I kind of regarded this as a 1D simulation. That means that every tunnel segment, cross passage, ventilation shafts, stations, fans, dampers, bypass dampers, everything was in this model. That made for a very large, very complicated model, and I started simulations. The first thing that I noticed, was, well, nothing. Simulations were starting, but then they were halting. Not crashing, just halting. I suspected this somewhere in the 1D calculation that there was some kind of loop. And my immediate suspect were the cross passages. Those are passages between the two tunnels. And in the 1D calculation, they are only used for air leaks between the tunnels. And theoretically, they could loop flow between themselves. Tried the simulations without them. That worked. But then, when flow was becoming substantial through the boundaries, I got access violations, like a lot. Now, the way that I understand it, an access violations means that the simulation is trying to access RAM that wasn't allocated to it. You can try to restart those simulations. It's not going to work. All you can do is check your setup, start from scratch. Tried a lot of things to solve that. In the end, I just got to the conclusion that my model was too complicated. So to simplify my model, I needed to take a look at pressure losses and the way that they were represented in the 1D calculation. First type of loss I want to talk about are head losses due to transitions in the flow. For example, when flow transitions from a tunnel to a station, some pressure will be lost, and that would be represented by a coefficient that I would define at the node representing that transition. So in a series of tunnels and stations, I would have many transitions, many coefficients, but for the calculation, it would be the same if I summed up those coefficients, I would get the same pressure loss. So I could do with less nodes, which brings us to ducts. Now, ducts are representing both tunnels and stations, and the loss the loss associated with ducts will be friction loss due to wall roughness. Now, I was looking at the parameters, I was looking at friction, and I saw that the friction between tunnels and stations is not that different. Considering that stations are much shorter than tunnels, that difference should be even smaller. So theoretically, I could use a single duct to represent both tunnels and stations, and I would get almost the same friction. And that brings me to the final setup. So in the final setup, what you see here on the right, there's a portal. And on the left, there's the edge of a station and a little portion of a tunnel. And in between, there are our HVAC components representing a series of tunnels and stations. We have at the nodes the head loss coefficients that I talked about, representing all the transitions in the flow, summed up together. We have a single duct. It's really small in the model, not like you saw in my early tries, but I configured it with the real length of the tunnels and stations, so it can be like 2-3 kilometers for the calculation of the friction. And now simulations were running, not crashing. That was a big plus for me. I slept better at night. I was getting results that made sense, and I would like to present some of those results. First, I would like to present some results from the station simulation. The first station that I employed the multiscale approach to, I used the ventilation setup recommended by 1D analysis. And I was seeing early on that smoke was rising from the platform to the concourse. Now what you see here, the graph up there represents the flow with a continuous line for the flow from the concourse, and the other two lines are the boundary flow that we are talking about. Okay, and under that there's a depiction of a station. The platform is at the bottom, and above that the concourse. You can see the smoke rising from the platform to the concourse. Now obviously this is not good for smoke control reasons, but I would like to highlight something else here. Smoke is coming up while air is coming down. That means that the flow is not one directional. So in this specific case, the 1D results are not valid. If I were to use those as boundary conditions in my model, my results may not be valid. So added a few fans, a lot more air, no smoke coming up, that's good. And I would like to take a minute to talk about the flow as it is represented with these graphs. So So first of all, between the initial and the final simulations, you can see that the basic behavior of the flow did not change. The amount of air obviously did, but what happens is fans start extracting in about 60 seconds. Now, the flow is going to start coming in through the concourse first because it has less pressure losses on the way to the fans. Okay? Tunnels have more pressure losses. We talked about them. So they will have a bit of a delay, and when flow starts coming in through the tunnels, then the flow from the concourse is going to start decreasing. But then there's an increase, both in the initial and the final simulation. That happens because we see one side of the station. That side, there's a burning train. On the other side of the station, there's another train. Passengers are alighting from that train. Once they are done alighting from the train, the doors close. So some flow that was coming in through the adjacent tunnel will stop. And the immediate compensation for that would be from the concourse, because less pressure losses, like we said. And then it continues decreasing, goes into really nice steady state flow there. Next, I would like to present some results from tunnels. And here, I would like to revisit my assumptions about the head losses and the friction. Okay? And I would like to do that by comparing FDS and SES results. SES is a subway environment simulation software. It's a 1D simulation software designed for vehicle tunnels. And I set it up so that tunnels would be tunnels and stations would be stations. Head losses at the right nodes, right? So no assumptions, just, you know, the way it's supposed to be. So first off, the first tunnel, with a dashed line, you see the SES results, as I would use them as a boundary condition. And the continuous line are the FDS results. So there's, first, with the FDS results, there's a bit of a delay from the tunnel boundary, and you would expect that, okay? And then at about 100 seconds, you see like a squiggle there, a bit of a decrease in the flow. That happens because a cross passage is opened between the event tunnel and the adjacent tunnel. The adjacent tunnel is overpressurized, so some flow is going to come in through the cross passage, reducing the flow coming in through the boundary. Then at about 600 seconds, that cross passage will close. All the passengers are at the adjacent tunnel safe, and the flow through the boundary will increase and converge into a steady state flow with a difference of less than 7% from SES results. Next, we have another tunnel. And here, again, there's a bit of a delay from the boundary. That is what you would expect. No cross passage here, just more perturbations. And it converges to the steady state flow of less than 2% from the SES results. So in conclusion, first, for engineering analysis purposes, I thought that I got very good agreement between FDS and SES. And the flow field that I obtained here with the multiscale approach was responsive to changes in the simulation. It could be explained physically, you know, all the changes that we saw in the graph. And all in all, I thought that this was a good representation of realistic flow in the transient phase. And since we are interested in the transient phase, that's when egress happens, I thought that this was very good. Questions? It is cold here.
So for your 1D portion of the model, I mean, how did you determine these, you know, loss coefficients and roughness factor, or whatever it is you needed to include in the one-dimensional model? I mean, a train tunnel is a lot bigger than like a pipe. So how did you deal with that?
So basically, I used the same settings that was used in 1D analysis, and they kind of assume the same friction for a station and a tunnel. Obviously, that's not that accurate, but okay. As for the area and parameter, I used the tunnel area and parameter because that would be the restriction geometric factor, right?
Okay, good, thanks.
That's really interesting. I haven't seen somebody use the HVAC model like that before. That's we usually use SES for that type of analysis, so that's really cool. When you were looking at how did you model like the losses off the ducting, or did you neglect like the heat transfer losses from like the hot smoke downstream in the 1D model?
Well, I didn't totally hear you. I heard about something about heat losses there.
Yeah, the heat losses in the HVAC model. How are you modeling that here?
So that's a good question. Obviously, I did not want any heat transfer through those boundaries. So basically, on the adjacent tunnel there, we're just used for, natural flow. And at the event tunnel, the boundaries were placed so that flow would only come in cold. Didn't want any, you can actually see it here. Didn't want any smoke. Yeah, you can't see my screen. This is a good example of this. We want only one-directional, strongly one-directional cold flow coming in through those boundaries.
Okay, thank you.
Other questions? Okay, excellent. Thanks so much for your talk. So good.